Welcome, dear students. Now we discuss question paper 2021, Unit-3, Mechanics paper, CC-10, Semester 4, Mathematics Honors. Question paper 2021, Unit-3. Question 4a. A particle is moving in a plane under the action of an attracting force to a fixed point in the plane equal to mu times the distance from that point per unit mass. The initial coordinates and velocity components with respect to fixed rectangular axis passing through the center of force are a, B and u, v respectively. Find the position of the particle at time t and show that the path described by the particle is this. This is the figure, no marks. So let a particle of mass m is moving in a plane under the action of attractive force of magnitude F is equal to m mu r. This is the attractive force. This is attractive force at this point P towards the fixed point O chosen as origin, where r is the distance of the particle P at any time t from O. Then the equation of motions of the particle, equations of motion, this component, actually x component is this m d2 x dt square equal to minus m mu x, because this force F is equal to force F is this minus m into mu into r. So F vector equal to this minus m mu minus for attractive force, this mu into r vector. R vector means x I cap plus y j cap, because this is the two-dimensional force planar motion for this. So component of A is this minus mu m mu x, and for the y component this m d2x d2y dt square equal to minus m mu y. Here mu is a positive constant. From equation 1 we get this d square plus mu bracket x equal to 0. This capital D stands for ddt, and the general solution we know from differential equation, this x equal to capital A cos root mu t plus b sin root mu t. This A and B are arbitrary constants. And from equation 2, similarly, we can find this general solution of 2, this y equal to c cos root mu t plus d sin root mu t. C and d are arbitrary constants. The initial positions, that is at t equal to 0, the particle is at A with coordinates AB. This point A starts from this point A at t1 t equal to 0, and corresponding initial velocity components along the x-axis capital U and along the y-axis capital B. So at t equal to 0, x equal to a, y equal to b, and velocity components dx dt equal to u, dy dt equal to b. And from 3, this equation 3, we use these conditions, and this we get this a small a equal to capital A. And from 4, using these initial conditions, we get b is equal to capital C. Differentiating with respect to t, 3 and 4, we get respectively integrate ddt x equal to this, ddt y equal to this. And using the initial conditions, this from dx dt equal to capital U, and at t equal to 0, so capital U equal to this, so b equal to capital U by root mu. And this dy dt equal to capital B at t equal to 0, so put t equal to 0 here, so b equal to capital B by root mu. So we find all the constants, capital A equal to small a, capital B equal to capital U by root mu, C equal to small b, D equal to capital B by root mu. Hence x equal to this and this from 3 and 4, put all these values A, B and C and D. So this gives the position of the particle at any time t. 6. Now the equation 6 can be P in equation 6 can be written as, so this is equal to a root mu cos root mu t, this multiplied by root mu, so a root mu cos root mu t plus u sine root mu t, this minus root mu into x equal to 0. And from this second equation of the equation 6, this multiplied by root mu on both sides, we get this. And by cross multiplication and solve for cos root mu t and sin root mu t, this for this. So this into this, u into minus root mu into y, and this into this, minus of this into this, so plus v into root mu into x, and similarly so on. So cos root mu t equal to this by this, and sin root mu t equal to this by this, and squaring, adding, we get cos square root mu t plus sin square root mu t equal to 1, and this square plus this square, so we get the required result. Next question, 4a. A particle moves in the curve y equal to a log sec x by a to the base e in such a way that tangent to the curve rotates uniformly. Prove that the resultant acceleration of the particle varies as the square of the radius of curvature. Equation of the curve is this: y equal to a log sec x by a by to the base e. This is the equation of this curve. Since the tangent to the curve 1 at any point P, this is the tangent PT, and this tangent rotates uniformly. This tangent rotates uniformly, and then so dt of psi equal to constant C, where psi is the inclination of the tangent PT with the positive x-axis in the anticlockwise sense, and differentiating one with respect to x, so dy dx equal to, we get tan x by a, equation 3. Again differentiating with respect to x, d2y dx square equal to 1 by a sec square x by a. The radius of curvature of the curve 1 at the point P, this rho equal to 1 plus y dy dx whole square whole to the power 2, 3 by 2 whole divided by d2y dx square. So put all these values from 3 and this d2y dx square. So we get rho equal to a sec x by a, equation 4. Now dy dx equal to tan psi, and this tan psi equal to x by a from 3, because this dy dx equal to tan x by a, so dy dx equal to tan x by a. So psi equal to x by a, hence x equal to a into psi, equation 5. Differentiating 5 with respect to t, and ddt of x equal to a ddt of psi, and this equal to a into c, because from 2, equation 2 ddt of psi equal to c, so put this a into c. Again differentiating with respect to t, we get d2 x dt square equal to 0. This a and c are constants. Again, now dy dt equal to dy dx dx dt. This dy dx equal to tan x by a, dx dt equal to a into c from 3 and 6. So this is equal to ac tan x by a, equation 7. Differentiating 7 with respect to t, we get d2y dt square. So this ac equal to this ac square sec square x by a, equation 8. And differentiating 6 with respect to t, we get d2x dt square equal to 0. Hence the resultant acceleration, this d2x dt square whole square plus d2y dt square whole square whole root over. So after simplification, we get this c square by a bracket a 6 sec x by a whole square. So this rho equal to from 4 rho equal to a 6 x by a, put value of rho here, so c square rho square by a. Hence this resultant acceleration is varies the radius of curvature square, because c and a are constants. Hence prove the result. Next question, 4 C. A gun of mass M fires a shell of mass m horizontally, and the energy of explosion is such as would be sufficient to project the shell vertically to a height h, so that the recoil velocity of the gun is whole root over 2m square gh by m bracket capital M plus small m. Let E be the energy of explosion, since this energy is sufficient to project the cell vertically to a height h. Hence, this energy must equal to the work done in raising the cell of mass m vertically to a height h. So this energy E, uh, explosion energy, is equal to mgh, potential energy mgh. And this is the acceleration due to gravity. And let u and v be the speed of the cell and speed of the recoil velocity of the gun. Actually, recoil speed is this gun, v, and u is the speed of the cell. Then by principle of conservation of linear momentum, this equal to mu equal to capital M into v. Capital M is the mm, mass of the uh, mass of the gun, and small m is the mass of the cell. So this U equal to capital M by small m into v. Now the energy of explosion equal to kinetic energy of the cell plus kinetic energy of the gun. So this is half mu square plus half capital M v square, and with the value of U, and after simplification we get E equal to this capital M bracket capital M plus small m by twice m v square. So v square equal to this. So v equal to this, put the value of E in gh. So we get v equal to root over of twice m square gh by m into bracket capital M plus small m. Put the result. Next part, question D. A uniform chain of length twice A is hung over a smooth peg so that the length of it on the two sides are L minus C and L plus C. Motion is allowed to ensue. Use principle of energy to show that the chain leaves the peg after a time. This. No figure, no marks here. This is the position A0, and this is the position B0, initial position. And so let small m be the mass per unit length, small m, of the chain, and x be its displacement at any time t, from A0 to A. This displacement at any time t, this displacement x, initially at t equal to 0, this chain is this initial, this chain at time t, this displacement, this side is upward displacement and this side is downward displacement. So this x, this distance is x, so this distance is also x. And the length of the chain on the two sides of the pulley are this. So this L plus C plus x, and this total distance is L minus C, initial distance in this side, and this L minus C minus x. So this distance is L minus C minus x. The depth of the center of gravity of the string below the pulley is below the pulley, and this the x0 bar is the initial center of gravity of this chain, and this x bar is this position is the center of gravity at time t. So x bar equal to this equal to we use the formula x bar equal to m x1 bar plus m1 x1 bar plus m2 x2 bar whole divided by m1 plus m2. So m1 plus m2 this is equal to 1 by twice m into twice L. L is the total length of this chain, and m is the mass per unit length. So total mass is this m into twice L, and this is the mass, unit mass into length in the left hand side, L minus C minus X, into this L minus C minus x by 2. This the height is this. So x bar for this side, center of gravity is the middle point of this. So this plus this mass m2 is this m into L plus C plus x for this length, right hand side length of this chain, and this length. So center of gravity for this length, this x2 bar, that is equal to this length divided by 2. So after simplification, we get twice L1 by twice L square bracket plus C plus x whole square equal to, that is equation 1. The initial depth of the center of gravity of the string is x0 bar. Actually, we are putting x equal to 0, no displacement. So x0 bar equal to 1 by twice L square plus C square. Hence, the work done by the weight of the chain, this is equal to work done, this is equal to mg into y1 minus y2. Actually, this twice Lm x bar minus x0 bar into g. The total mass is this twice Lm, and this is the g, and y1 minus y2 is this x bar minus x0 bar. So put all these values x0, x bar and x0 bar from 1 and 2. After simplification, we get mg bracket x square plus twice cx. The change of kinetic energy in the chain, this kinetic energy, final kinetic energy minus initial kinetic energy. So final kinetic energy is the half of mass into velocity square minus initial kinetic energy at the rest. So this 0. So we get Lm dx dt whole square, equation 4. The principle of energy conservation, change in kinetic energy equal to work done. So change in kinetic energy is Lm dx dt whole square, and work done is this mg into x square plus twice cx. So we get dx dt equal to root over of this positive sign here taken because dx dt increases with the increasing time t. Let capital T be the time of the chain takes to slip off the pulley. So this left hand side part is the upward direction. At some time capital T, and this point A is at this point. So this chain lead off from the pulley. So this is equal to slip off from the pulley. This 0 to capital T dt, and this from this root over L by G integration 0 to L minus C dx whole by root over x plus c whole square minus c square. Actually, this x square plus twice cx equal to x plus c whole square minus c square. This the log of this after integration, this root over of x plus c whole square minus c square, limit 0 to L minus c. So after simplification, we get this total time t capital T equal to root over L by G log of this. Proved. This is the unit 3 completes 2021. Thank you for watching this.